Now let us take a look at some examples related to hydroelectric power station. Number one, example 2.6, a hydroelectric station generating station is supplied from a reservoir of capacity 5 into 10 power 6 cubic meters at a head of 200 meters. You have to compute the total energy available in kilowatt hour if the overall efficiency is 75%. Number one, in order to get the energy which is stored at this height of 200 meters, you have to use the formula that is mgh. So in that formula, m is the mass. So you have to find the mass of this amount of water. So if the capacity of reservoir is 5 to 10 power 6 cubic meters and the density of water is 1000 kilograms per meter cube, or 1000 kilograms per cubic meter. So if that is the density of the water, then the mass of the water will be equal to the density multiplied by the volume of the water. And let us look at the solution of this problem. So density of water is 1000 kilograms per cubic meter, which gives the mass of the stored water m as m is equal to 1000 into 5 into 10 power 6, which is the volume of the water. So that comes out to be 5 into 10 power 9 kg. So the mass of the water which is stored inside this reservoir is 5 into 10 power 9 kg. Now you can use the formula mgh to see how much energy is inside the stored water. So hydro energy available from dam is mgh, and that is 5 to 10 power 9, g is 9.8, and h is 200. So that will give you energy in joules or watt seconds. So the energy in watt seconds is 9.8 into 10 power 12 watt seconds. So you have to convert this watt second into kilowatt hours. So for to convert it into kilowatt seconds, you have to divide it by 1000, and to convert this second into hours, then you have to divide it by 3600. That is what is being done here. You have to divide this 9.8 into 10 power 12 by 1000 and 3600. So by doing so, you get the energy, hydro energy, that is available from dam as 2.72 into 10 power 6 kilowatt hours. But this is not the energy which was required from us. They want to know how much electrical energy is available in kilowatt hours. So to get the electrical energy in kilowatt hours, we have to multiply this total available hydro energy with the efficiency, overall efficiency of the plant. So that is 75%. So 75% of this energy will be available to us, and that is found from this formula as 0.75 into 2.72 into 10 power 6, and that gives us 2.042 gigawatt hour energy which is available from this plant. So 2.042 gigawatt hour energy is available inside that plant, and this is the electrical energy which we can produce from this plant of the given specification. Now let us look at another example. It has been estimated that a minimum runoff of approximately 94 cumex will be available at a hydraulic project with a head of 39 meters. So you have a hydroelectric power station, you have a dam, and it is approximated that the minimum runoff will be approximately 94 cumex, and the head is 39 meters. So the dam has been constructed and the water is stored at a height of 39 meters, and the water flow rate which is available to you from this dam is 94 cumex. Now, as I have told you previously, cumex is equal 1 cumex is equal to 1 meter cube per second. So this 1 meter cube of water will flow out of the dam every second if the flow rate is 1 cumex. But in our case, it is 94 cumex, so 94 meter cubes of the water will flow out of the dam every second. So you have to compute the firm capacity and yearly gross output, assuming plant efficiency of 80%. So let us take a look at the solution. What is required of us? So number one, a water flow rate, the or mass flow rate of the water, as I should call it. How much mass of the water is displaced every second can be calculated from the density of the water, which is in kilograms per meter cube, and the flow rate which is available to us, 94 meter cube per second. So if you multiply these two, you will get the mass flow rate of the water, how much mass of the water is displaced in each second if this flow rate is available to us. So 94,000 kilograms per second of water will flow. So let us now talk about the available hydro power which is inside the plant. So if you take the formula mgh, that is the formula for energy, and if you substitute the mass inside that energy formula with mass flow rate, you will get what is called power, because power is the rate of flow of energy. So mass flow rate into gravitational force into H will give you the available hydro power inside that reservoir. So 94,000 kilograms per second into 9.8 meter per second squared into 39 meters will give you the power in watt, and that comes out to be 35.927 megawatts. So this is the gross firm capacity, gross plant capacity which is available to you. So this is the hydroelectric power which is available, hydropower which is available inside the dam, and this is also termed gross plant capacity. Now you have to find out firm capacity, which you can easily calculate by using the plant efficiency. By firm capacity, which we mean how much electrical energy will come can be taken from this plant. So you simply multiply the gross plant capacity with the efficiency to get the firm capacity. So firm plant capacity is equal to plant efficiency into gross plant capacity, or 0.8 into 35.927 megawatts, or 28.741 megawatts. So firm plant capacity is 28.741 megawatts. So this plant is able to give you 28.741 megawatt. Obviously, it is it is a small hydroelectric power plant. So how much energy can you produce in a year is what we call yearly gross output. So yearly gross output can be calculated by multiplying the firm plant capacity with the number of hours in a year, or number of hours in a year for which the plant was in operation. So if I give you the number of hours for which the plant was in operation, then you cannot use 8760. Then yearly gross output will be those number of hours which I have given you. So I'm going to correct myself here, and I'm going to tell you that if I ask you about gross output, you will always use 8760, because gross is something which is which you can get if the plant runs for all the time, and net is something which you get actually. So if I give you a number of hours of operation and I ask you about net output, then you should use the number of hours the plant was in operation. But if I ask that you calculate the gross output, then you should use the and all of the hours in a year. So in this case, we are asked gross output, so you should use all the hours in a year. But if I ask you that you have to calculate net output, yearly net output, then you can use then I will also give you how much time the plant was in operation during the year. So from this we get the yearly gross output as 251.775 gigawatt hours, or 252, around about 252 gigawatt hours. Now let us talk about another example. So water for a hydroelectric station is obtained from a reservoir with a head of 100 meters. So head is 100 meters. You have to calculate an electrical energy generated per hour. So electrical energy generated per hour, which is similar to saying you have to electrical energy is normally calculated in kilowatt hours. So per hour means kilowatts. So you have to find out how much electrical energy is produced per hour, or you can have to find out the power in kilowatt. Another data which is hidden inside this statement, but you cannot see it, is it is requiring that you calculate the electrical energy generated per hour per cubic meter of water. So it is already giving you the water flow rate, which is 1 cubic meter of water per second. So if the hydraulic efficiency is 0.86 and electrical efficiency is 0.92. So keep in mind that hydraulic efficiency being 0.86 and electrical efficiency being 0.92 will give you the overall efficiency, which is the product of these two. Overall efficiency will be equal to 0.86 into 0.92. So let us write all of the data which is available from this statement. So water head is available to us as 100 meters, which is over here. Then the discharge is 1 meter cube per second, which is over here. Then overall efficiency can be found from multiplying these two efficiencies, which we are doing here. So 0.79 is the overall efficiency. So how much weight of water is available to us? So we simply have to multiply the flow rate of the water with the gravitational force and the density of water. So density of water is 1000 kilograms per meter cube, and the flow rate is 1 meter cube per second. So 1000 into 1 is 1000 kilograms per second of water. 1000 kilograms of water will displace every second. So we are multiplying it with 9.8, the gravitational force, to get the weight of the water in newtons. You already obviously already know that the mass is written in kilograms or grams or the units of mass, and weight is described in units of force, because it is the force which is by which you are being pulled towards the center of the earth. So we get the weight of the water available every second, which is 9810 newtons. So the power produced by this dam will be weight into height, which is the head, which is 100 meters, into the overall efficiency. So this power is the electrical power which will be produced. So 9810 into 100 into 0.79 watts, which gives you 775 into 10 power 3 watts, or 775 kilowatts. So energy generated per hour will be 775 kilowatts into 1 hour, which will give you 775 kilowatt hours. So energy generated every hour will be 775 kilowatt hours, but power will be 775 kilowatts. Now let us move on to another example. So you have to calculate the average power in kilowatt that can be generated in a hydroelectric project from the following data. So catchment area for the water, where the water will be stored, the catchment area is 5 into 10 power 9 meters squared. The mean head of the water storage is 30 meters. So obviously the water storage has different heights at different points, but the mean height is 30 meters. Annual rainfall is given by F, and it is 1.25 meters. So 1.25 meters annual rainfall is the annual rainfall. The yield factor is 80%. What do we mean by this yield factor? So the total rainfall in any area cannot be utilized, because part of it is lost due to evaporation, or part of it is lost due to absorption by the ground. So all of the water which fell from the due to the rainfall cannot be utilized. So a portion of it can be utilized, the remaining is lost. Yield factor indicates the percentage of rainfall available for utilization. For example, in this case, 80% yield factor means 80% of the water which came from rainfall is available for use to generate electricity. So keep this in mind. So the overall efficiency of the plant is given 70%, and the load factor is given as 40%. So remember that load factor is equal to average load divided by maximum demand. It is asking you what is the rating of the generators installed. So you have to determine what rating generators must be installed inside this power plant, and that is where this load factor will come in handy. It will give you the maximum demand based on the average load, and this maximum demand needs to be satisfied at whenever it comes on the plant. So your plant rating will be in conjunction with this maximum demand. So the plant rating should be able to meet this maximum demand. So let us look at the solution. So volume of the water which can be utilized per annum is given by catchment area into annual rainfall into yield factor. This is obvious now, that yield factor is the total amount of water which is available to be used to produce electric power, and annual rainfall is also given to you, catchment area is also given to you. So this much volume of water is available for use to generate electricity. So weight of water available per annum can also be found from this data, and using the density of water. So weight is given by 5 into 10 power 9 meter cube, which is the volume of water, into 1000, which is the density of water, kilograms per meter cube, and this is 9.81 meter per second square, which is the force of which is acceleration due to gravity. So weight of water comes out to be 49.05 into 10 power 12 newtons. Now electrical energy available per annum can be calculated from this formula, WH into overall efficiency. So overall efficiency is given to you as 70%, H is given to you as 30 meters, and W you have already found. So substituting all of these values, you will get energy in watt seconds, and you have to convert it into kilowatt hours. So you have to divide by 1000 and 3600. So you get 2.86 into 10 power 8 kilowatt hours worth of energy. So number of hours in a year are 8760. So let's assume that the plant remains in operation for all of those hours. So so the overall power, the average load on the average power which the plant is able to produce is 2.86 into 10 power 8, which is the energy, divided by the number of hours for which it was during which this energy was generated. 8760, that gives you 32648 kilowatts. Now you also know that the maximum demand on the power station is given by average demand, average load divided by load factor, because load factor is equal to average load divided by maximum demand. So you just simply cross multiply the terms. So maximum demand is equal to average demand divided by load factor. Average demand is given by this, which you have calculated, divided by load factor will give you the maximum demand which will arrive at this station. So load factor for any station is already defined. So this data will be available to you at all the times, that the load factor on this power station is 40%, and that is based on the data which we get from the field. So 40%, if the load factor of a plant is 40%, then you can simply find out the maximum demand by using this formula. So maximum demand came out to be 81,620 kilowatts. So maximum capacity of the generators should be 81,620 kilowatts, and you can employ multiple units of generators to whose aggregated power is equal to this power or greater than this power. So there can be some reserve capacity can also be kept in a plant which is not utilized, but there to service if the load on station increases beyond the estimated limits.